Hi, today we're going to be going over problem 3 from the first round of IGMO 2020. Note that this was problem 3, so this was supposed to be one of the hardest problems, and if you do look at the statistics, this ended up being the second hardest problem. But what is IGMO, you may ask? Well, more on that later. The question says, for k positive reals, x1, x2, all the way up to xk, that sum up to k minus 1, or rather their n minus 1th powers sums up to k minus 1, prove this monster. And now note that n is strictly greater than 1 here and k is greater than or equal to 2 here. How do I know this? Well, because I proposed the problem. More on that later. So if you want to give the problem a try, go ahead and do so now. While you're busy trying the problem out, let me actually tell you about IGMO. So IGMO is an online free-to-enter mathematical Olympiad, and this year they're going again. This time though, they've got a $2,000 prize pool for the winners, and you can register very easily by going to igmo.info, this link is also in the bio, and clicking on register. All you have to do is fill a form, enter all these necessary details, and just click on register, and you'll be registered for the exam, the first round of which is on the 21st of May. So on the 21st of May, you'll have 24 hours to access the paper, and once you access the paper, you have 4 hours to submit your solutions. Those who score well in the first round get to go to the second round. And note that this is all free of charge. There are no hidden costs. It's completely free to participate. Now that I hope you've given the problem a try, let's solve it. So the nicest solution that I have in mind is actually with Chebyshev's inequality. Let me just restate what that says. It says that if you have a monotonically decreasing sequence like this, all the way up to an, and then same thing for bi, so it goes b1 greater than or equal to b2 all the way up to bn, the following inequality holds. And the way I remember it is that the mean of the product sum is greater than or equal to the product of the means. And this is, well, they have the same parity in terms of decreasing or increasing. Well, now this might look a bit weird because I don't instantly see where we have any decreasing or increasing sequences here. But note that we have a symmetric expression over here. See, this one is x1 to the n, and the bottom is, well, it's the sum of all of the variables, but x1's not there. Same thing goes for here, but this one's just with x2. And it's symmetric in the sense that it does not matter which xi is where. I can reorder it and it's still the same sum. So what I can say is that, well, let's just say up to reordering x1 is greater than or equal to x2 is greater than or equal to blah 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 xk. And I can assert this because I have a symmetric expression, and this is a common technique sometimes that might help. And it helps here because now I have one decreasing sequence, okay, but note that I also have a product sum in my expression here, so perhaps I should try to get a decreasing sequence for the denominators here. Right, now that I've said that x1 is the biggest out of the two, it seems kind of clear that, okay, well, if I have the sum of all the other ones that with x1 removed, that's going to be the smallest one, you know, if you compare it to, let's say, one here with x2 removed, well, that one's going to be a bit bigger, and so on and so forth. So I actually get another chain of inequalities. Let me write that out. Namely, the chain of inequalities I get is that x2 plus dot 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 all the way up to xk, so this is just the sum with x1 removed, is less than or equal to x1 plus x3 plus dot 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 all the way up to xk. This is just the sum with x2 removed, and this continues on up until the last one, which is x1 plus x2 plus dot 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 xk minus 1. Okay, but I've got this in the opposite parity. Well, I can just take the reciprocals, and good thing for me, I actually get that 1 over this is, well, now it's going to change to greater than or equal to, so I have now a chain of inequalities for the denominators, which is exactly what I wanted. So let me just write that out. It goes like this. Okay, so now I'm actually in the prime position to apply Chebyshev's inequality. So let's just go ahead and do that. And note that I've actually got x1 to the n in the numerator. So I'm going to apply it on x1 to the n, x2 to the n, and xk to the n. But I still, of course, know that this itself is true. And I'm actually going to use that later. So applying that on this expression gets me, well, something that looks a bit beastly, but I'm gonna write it out. It gets me that x1 um, to the, well, okay, first off, the product sum on the left hand side, that's just the expression we've got in the problem. Let me just call that expression s, I guess. And so, well, that just tells me that I've got s over, and there's k variables here, not n, is greater than or equal to, note that I can just cancel out the k's, so this is just going to say ks is greater than or equal to, now I've got a sort of tough expression to deal with. I've got x1 to the n sums up all the way up to xk to the n, and now on the right hand side I've got 1 over x2 plus dot 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 xk plus dot 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 1 over x1 plus dot 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 xk minus 1. This is just, of course, all of these terms added up. Okay, let me just multiply some stuff in. Note that, for example, if I had multiplied this in, and then I had multiplied this in, and if I just, if I wrote out x2 to the n as well, and here, for example, if I wrote out x1 plus x3 plus dot 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 all the way up to xk, and if I multiplied that out as well, note that if I just looked at those type of multiplications, I'd get a copy of s, and I can move that copy of s to the other side. And so that would give me k minus s is greater than or equal to, and then the remaining stuff. And so now you might ask, well, what is the remaining stuff? The remaining stuff actually turns out to be quite nice because, well, I've put in x1 to the n only in this term, but I've also got to put it in this one, and I've also got to put it in this one, and I've got to put it in the remaining ones. Okay, that's fine, but note that I've also got x2 here, and I've also got x2 here. It's just not in this one. Note that I've also got xk here, and I've got xk here. It's just not in the last one. And so you see that I'd actually be able to combine them together into one numerator because a lot of these are going to share the same denominator. And in fact, I'd actually get that the right hand side is, well, if you expand it out with some algebra, you can do that if you want, but trust me on this. It's going to be this expression right here. So it goes x1 plus dot 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 xk minus 1, and then there's the one for with x1 removed, so that's x2 to the n plus dot 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 xk to the n over x2 plus dot 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 xk, and then it goes on, and there's the one with k removed, so that's x1 to the n plus dot 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 xk minus 1 to the n, x1 plus dot 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 xk minus 1. And you can convince yourself that this is true because the one with where x2 goes into the one where x2 is not in the denominator, well, that's already been moved to the left hand side, and so now I've only got expressions where x2 is both in the numerator and the denominator, and well, that's what I see here. And so I'd be left with expressions of these type. Okay, that's still not very nice because it seems as though I've made the problem more complicated, but here's where the problem is actually quite beautiful. So note that the condition we've been given is that x1 to the n minus 1 plus dot 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 all the way up to xk to the n minus 1 is actually equal to k minus 1. And note that I've got a k minus 1 on the left hand side as well. So perhaps all I need to show is that this thing is just greater than or equal to this. And so now perhaps your spidey senses are tingling. This looks a lot like Chebyshev again because, well, I've got x1 here, and I've got first powers of the xi here, and I've got n minus 1th powers. And if I multiply them together, I've got nth powers of them. And Chebyshev does let me multiply them together. Oops. Let me just show it again. It does let me multiply the sequences together. It helps me take a product sum. So I'm actually going to apply Chebyshev here again. Note that I'm going to this time apply it on x1 to the n minus 1, which I know is bigger than or equal to x2 to the n minus 1, which this continues on to xk to the n minus 1. And now I'm going to apply it on x1 all the way up to xk, and I hope to retain something of this form. So, well, let me just apply Chebyshev's inequality again. And yeah, that's the formula. It goes like this: xk to the n. I'm just going to move the k to the other side, so it's going to be k here. And now this is greater than or equal to the product of the sums, which is, well, this one's just x1 summed up to xk, and this one's just x1 to the n minus 1 summed up to xk to the n minus 1. It looks like we're almost done, but note that I don't actually have it going up to k here. In these terms, each one I've got only going up to k minus 1, or it's got one of them removed. So I actually have to apply Chebyshev's inequality separately to each of these terms. So let's just to illustrate what I'm saying. Yes, I do have this inequality, but I can't directly substitute it here because, well, none of these terms are, in this expression. What I can do now is, let's say I only considered it up. Let's say I only considered the Chebyshev's inequality for this term. For this term, I'd have to go up to k minus 1. Same thing here. And, well, now I'm going to be able to substitute it because note that I can just move the sum of the first powers to the other side, and this one just becomes k x1 to the n plus dot 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 xk minus 1 to the n over x1 plus dot 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 xk minus 1 is greater than or equal to x1 to the n minus 1 plus dot 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 all the way up to xk minus 1 to the n minus 1. I actually don't know what this evaluates to. I only know that the sum with xk to the n minus 1 xk to the n minus 1 evaluates to k minus 1, but I actually don't know what this evaluates to. Well, that's okay, because I've only applied Chebyshev to one term now. And actually, this is again where the problem is quite nice, because let's say I applied it here, and I also applied it here with the corresponding k minus 1 terms. Oops, yeah, I actually have applied it to k minus 1 terms, so I have to change this to k minus 1 here. Forgot to change that when I was only applying it to k minus 1 terms. And what I'm going to get is, well, I'm going to get another Chebyshev's inequality of this form. It's going to be, let's say I considered the one with x1 removed. I'd get x2 to the n plus dot 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 all the way up to xk to the n, all of that over x2 plus dot 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 xk greater than or equal to x2 to the n minus 1 plus dot 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 xk to the n minus 1. And I now apply k minus 1 Chebyshev's inequality. Apply k Chebyshev's inequalities, each one with one of the variables removed, and I get terms of like these. And note that if I sum all of them up, I actually get k minus 1 times what I have on the right hand side here, this expression. Let me just say that that expression was, I don't know, m. I'd actually get k minus 1 m. Well, now it's greater than or equal to, and note that because I had k sums, but in each sum, one was missing. So let's say x1, for example, it's missing in only one of the k sums. So it's going to be repeated k minus 1 times. So I actually get that this is going to be k minus 1, and each variable is repeated k minus 1 times. So this one's going to be x1 to the n minus 1 plus dot 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 all the way up to xk to the n minus 1. And good thing I know what this evaluates to. This evaluates exactly to k minus 1. And so now I have that m is going to be greater than or equal to k minus 1. Okay, but wait, that I think the problem is just done, right? Because we know that k minus 1 to the s is greater than or equal to m. Well, that's greater than or equal to k minus 1, and so therefore we have that s is greater than or equal to 1. Wow, that was quite a large problem, but actually quite liked how all of it worked out, and this was why I actually proposed it to the IGMO as well. I'm part of the problem selection committee of IGMO, which is the International Gamma Math Olympiad, and IGMO is just run by a few math enthusiasts. We call ourselves Gamma, and during 2020, when COVID happened, most contests were not going because everyone was in quarantine. So we just decided, well, wouldn't it be fun if we had an online contest that was free to participate in, that anyone could take part in? And it actually turned out to be a huge success. We were expecting like what, a few hundred participants, but it turned out that we had 2,500 plus participants. And so Jane Street saw that and they gave us a sponsorship this year. And so now there's a $2,000 prize pool. So, well, if you're good at this stuff, I'd definitely say register. Even if you're not good at this stuff, I'd also say register, because I remember last year the participants said that they had a lot of fun and they were able to experience an Olympiad when, well, some of them were too old to participate in Olympiads, or they got into math too late, or maybe their country didn't have the opportunity to give them an Olympiad, or maybe their prime Olympiad days were during COVID when they never got to sit an exam. So, participate for the sake of the experience. Join the Discord in my link. In the description. Just join the Discord there. You're gonna find like-minded people who love to solve math problems for fun. There's not many of those, and IGMO is one where they all get together and just try out their best. And if you do well enough, perhaps you might win some money. But the most important thing is that you get some very nice experience into Olympiad mathematics and you have a very fun time. Last year was amazing, and I'm sure this year is going to be amazing as well. The first round is on the 21st of May. I'd say register if you want to, but you definitely should. Tell your friends to register, tell your granddad to register, and yeah, it's going to be a great time. I hope to see you all on the 21st giving the exam. Best of luck to those who do register.